is gonna be, anybody remembers what happens to the Fourier transform? We just repeat it. We shift this basically to this frequency f1. We can also call it fc, like frequency of carrier. So it's like a carrier frequency. So we shift it to f of c, and then minus f of c. And I think there's a half here also. It's a scale by half. So the same thing here. So here is 0. Just shift it to f of c and minus f of c and the scale. And this is what we call modulation. So basically, we are modulating this signal g of t. And this is what happens. And now then we talked about, okay, now how can I get the signal, original signal back? Let's say I modulated my signal. I send it somewhere, and then at the receiver, I want GT back. Okay, what do? I have to basically, again, shift this spectrum back to this. So we know the shifting is basically multiplication by cosine. So multiplication by cosine or sine basically shifts the spectrum. So if I multiply this again by another cosine, what happens? I shift this to the right by fc. So instead of fc now I have 2fc, and minus fc goes to here, and shift it to the left. So we get minus 2fc, and another one here. So this is what happens. Okay, now this looks like exactly like my g of f. So I can put a filter, let's say here, and then extract my seed. Okay, so this is what we talked. We talked about the other time. Is it clear somehow? So just make sure that you remember, when you multiply a signal by cosine, you basically shift the spectrum. Yeah, and then if your cosine has a phase, like theta naught, you shift it and also multiply by each one phase theta naught, and then the other one e minus theta. And if this is now, if you have different signals, and then you modulate it with different higher frequency. Multiply this by cosine of 2 pi f1, t, multiply this by cosine of 2 pi f2, and then this one with another frequency. So basically you shift it with different amount. That's how you can hack several information in the frequency. They are separated in the frequency. Okay, so this is another example of shifting GF to the frequency f naught and minus f naught. And now the demodulation, as I mentioned, just multiply again by another cosine. So now let's mathematically see what happens. In the modulation, I have GT times cosine, one cosine. And then at the demodulation, multiplied by another cosine. So now I have GT times cosine squared, right? Okay. So multiplication by cosine, remember, is just shifting this to the left, shifting this to the right. So if you call that one, let's call this. Let's call this G, capital G M, like a G of modulation. Okay. This two replications. Okay. Now if I multiply this by another cosine, now I have to shift G of GM to the right and to the left, right? So basically I will get GM f minus f naught, and then plus GM f plus f naught. Okay. So do the upper again upper rule. Instead of f, replace it by f minus f naught once, and then f plus f naught. Okay. So f minus f naught here, and then another term f plus f naught. So that's why you get 4 terms. This is the the first, let's say apple. Because here instead of F, we put F minus F. Yes, F minus F naught. And then you have to replace it with F plus F naught. This is the second step of that. Okay. So just see what we have. Let's do the math. If now we have question.
Well, when you do that, you only get half the answer to the original signal.
Yeah, you multiply by 2. That's all. Yeah, that's very easy. Okay, so now you get F of minus 2F naught. Just do the math. Very simple addition. Here this F naught and minus F naught cancel each other, and then we have F plus. So this is exactly what we predicted in the with the graphical method. See, we have now G of F, and then F minus 2F naught. Remember, we ended up with 2 of the frequency, and then minus 2F naught. Okay, so again, this was after one cosine multiplication, F naught and minus F naught. After one cosine. Originally, this was the original signal G of F. This is after multiplication by one cosine. Now, this is after twice cosine. So this is one times cosine and another times cosine. Shift this to the right, shift this to the left. That's how you get 4 times GF, F minus 2F naught, F plus. Okay, and this is the Victoria. Any question here? Yes.
When you multiply by cosine, it shifts both of them like out, right?
Both of them to the left, both to the right. Yeah.
Then where does the one in the middle come from? Because I thought you were going to shift it to the right and then shift it to the left. That's how you would get the one in the middle.
So, see, if you shift these once to the right by F naught.
Right, so then
This will go to where? To F
to
naught.
F naught, right?
Where does this one go?
That one will go to the center.
Exactly.
I get that. So
Okay.
my question is, when you multiply by cosine again, does it shift it to the right again? What makes it shift to the left this time?
Yeah, both of them. Every time you shift both to the right and to the left. See? Okay. So what happens to this one? I shift it to the right and to the left. Oh. Because see the formula, it says G of F minus S naught plus G of F plus F. But once you multiply by cosine, you have to shift both directions.
Okay.
That's why when you have GF like that, original signal after multiplication by cosine, you have not two of them.
I see. So when you do
Shift to the left and shift to the left.
okay.
Now, after multiplication by another cosine, shift the whole thing again to the right. This will go to
Right.
12. This one goes to center. Now shift to the right, to the left. This one goes to 12. This one goes again to center. Now, that's why in the center you have twice of that.
Gotcha.
And then let's say, I don't know, if this was half and half. Now, this is half, this is half.
That's 1/4.
Actually, 1/4, because again you multiply by half. But this is half,
Okay.
because this is twice of that. Added, see, twice. This one and this one. Everybody get it? Right? If you don't get it, please let me know. That because I don't want anybody to miss this. Very important steps. This multiplication by cosine. Shift to the right and left. Another time shift to the right and left. That's how you get it.
When we're saying half, we're talking about the energy, right?
Yes, because the half comes from here. See? This is half. is that your spectrum now is like divided in two parts, so that's a little bit half and half. You know, just like always break it that way. So if this is one, so half of this is now in this part and half of that part. And then you do that again, half, so you get quarter here, quarter there, but then 12, this is basically quarter plus quarter at the center, the 12.
If you just multiply by 2, it'll be the same as the original.
Yes, just multiply by 2. Put a filter here and then multiply by 2, just run it, same as original. Yeah, so, or you can instead of multiply by cosine, just multiply by twice cosine, you get the same thing. So multiply by twice cosine, I'm passing the signal through a low pass filter. Why low pass filter? Because now, this is like a high frequency, this is also like a high frequency, it's a mirror of that, and this is low frequency. So low pass filter basically selects just the low frequency part and doesn't select those parts. If you do that, then you get this. So this was the analysis somehow in the frequency domain. Or you left the frequency domain, but even in the time domain you can do that. So originally I had GT, and then I multiplied by twice, basically 2 cosine. So I have cosine squared, and now basically use this formula, very simple formula that we have cosine squared is in terms of cosine of twice the angle. If you do that, so what you get is GT times 1 plus cosine of twice the angle, so instead of 2 pi, you get 4 pi. Just multiply, so you get GT, and then GT cosine of, okay, inverse. So what's the spectrum of that? If you look at the spectrum, it says in the time domain you have GT. So the spectrum is just the original spectrum. And then you have GT cosine of 4 pi. How does this one look like? Anybody can tell me? If I multiply this by this cosine, where do I get the replication? Where do they go?
Is it 2 over?
This is 4 instead of
4. Oh, it's 4 over. It's like shifted.
shifted where?
It's to the right, correct?
How much? 2 x.
That's what I thought.
Yeah, because if you had cosine of 2 pi f naught, it shifts to f naught. Now if you have cosine of 4 pi, it's like 2 pi times that, right? So it's shifted to 2f. Yes, this is the frequency. Yeah, this is the frequency. So basically, the error like this, if I had 2 pi f naught, it would go to f naught. I had twice the frequency, so it goes to 12. And now you add them, you know the addition. So this is exactly what we got from the frequency domain, but it's in the time domain. See, here was the frequency domain, you had one of the three of the original and then 2 x naught and minus 12 now. So from this simple formula that we had, cosine squared and then double the angle, double the frequency, you get the same. Everybody got it? So again, nothing to memorize here, just I understand. So I expect to spend 2 or 3 minutes per slide to understand things. And the best is if you just put it together. Maybe, I don't know, have a group study together, somebody remembers something, another person remembers another thing, and then discuss things together to understand them. Question? Okay, so we are done with the modulation for now. We are going to have one whole chapter on the modulation. Here we just studied the application of the Fourier transform. Okay. Now another property of Fourier transform. Let's find the Fourier transform of a periodic signal. Okay. So far we know that if I have a periodic signal, what can I get? If I have signal g of t, which is periodic. What can we get from periodic signal? What Fourier series, right? So far we have studied Fourier series.
So are you gonna use a low pass filter or do you just the transform for just one period of that series?
No, we are gonna not access transform also.
I thought that you only use Fourier transform if it's a single period though.
Right, that's why we are extending the notation. Yeah, that's why I'm just be patient. Wait. Yeah, so far for periodic signal, it was only Fourier series, and let's say if it was exponential Fourier series, we would represent it with some bns. Remember, we had, for example, b0, d1, d2, and it was discrete. Remember, 0, 1, 2, etc. So this was corresponding to the f naught there. What's f naught here? What did we call f naught? Yeah, harmonics of fundamental frequency, which comes from the signal being periodic. Good. So this was what we had studied for periodic signal. We had dn. Now here, like basically what we want to study is we say, okay, you know, we have a formula, we have a Fourier transform, we have some definition, gf is integral of gt minus j pi dt. Why don't we apply this periodic signal and see what happens to the Fourier transform, what happens to this formula, okay? And we do that, and now I'll just give you the final result. Is that interesting? The Fourier transform is gonna be bunch of deltas. So instead of dn's, we're gonna have some deltas. We're gonna prove this. By the way, in the midterm that we had one question that, let's say for example, you had to represent 5 times delta t minus 2. And a lot of you had to represent something like this. Right? So there is a huge difference between this and the actual thing, which is like represented by an arrow. So this one says, okay, I have a signal at time 2, and the amount of signal is 5. Let's say just 5 volts. Very simple signal, something finite, very simple, okay? This one said, at the time of 2, I have a signal which goes to infinity, okay, and comes back. Now, what is this 5 that we say? The 5 is basically the integral of that, the area, okay? So huge difference between this and that. That's why I just subtracted 2 points. But from now on, please just be careful about the way that you draw things. This is just simple value. This is impulses. Okay. So now let's start this. Okay, so my GT again is periodic. I know I have a Fourier series for that. Fourier series says I can write g of t as summation of dn e to the power of j 2 pi f naught t, right? And then now let's do the Fourier transform based on the formula that we have. So this is g of t. Now take the Fourier transform. When you take the Fourier transform, see this is a linear operation, right? I'm adding some terms. So when I take a Fourier transform, the Fourier transform is a linear operation. So I can write this as the, what do you think? If I have, for example, first term, second term, etc., I can write this as Fourier transform of the first term plus Fourier transform of second term. Why? Because superposition are linear. Right. So therefore, when I put an F, big F here, take the Fourier transform of that, I cannot take the Fourier transform inside, and then dn's are some coefficients. So, okay, so let's say you have d0 and then d1, e to the power of something, and then d2, e to the power of something else, etc. So I can write this as Fourier transform of d naught plus Fourier transform of d1 times that exponential. But d1 is constant, so Fourier transform and then d2 Fourier transform, etc. So this is coming from linearity of superposition. You can distribute Fourier transform inside, and then these are constant coming out of the Fourier transform. So this is nothing but that. See sigma dn here. Fourier transform. Dn and then the Fourier transform of the rest. So this is sigma dn Fourier transform of that exponential. Okay, now we know the Fourier transform of this. The Fourier transform of complex exponential is this delta. If you go to the table and you study this in the class, for exponential term, you have just the delta. So you have e for j 2 pi n dot t. The Fourier transform is the delta f minus n. Okay, good. So therefore, instead of these guys, I have to put the delta. So now this is the format that we get for the Fourier transform. So please make a note here that basically we use the linearity. Yeah, question.
No, we do it for this periodic signal. That's just for one period or all periods?
No, all three. All three. So if it was just the one period, then it was the usual Fourier transform. But here, no. Okay. So for this signal, which was periodic, if that was the Fourier series, from this formula, see, it says instead of dn just being alone, multiplied by corresponding delta. So d0 is multiplied by delta f, d1 is multiplied by a shifted delta by f naught. Okay, so now what is the interpretation? Interpretation is that, this is for example, right? When you have a periodic signal, periodic, remember we had fundamental frequency and then all the harmonics. These are only frequencies that are DC, these are all the frequencies. So therefore, when I take the Fourier transform of the same signal, see there is none of these frequencies are available. Okay, and none of these frequencies are available. The only things that are available are 0, f naught, to f naught. But then, instead of having this just discrete values, I have this delta. So does it make sense? So I don't have any, for example, of this frequency in between. Because this was a periodic, and I know the periodic signal only have this frequencies available. Therefore, it has to be again discrete. But then instead of just these guys, they have the delta. So this is a Fourier transform, therefore, for a periodic signal. So for periodic signal, we always have this delta function. Okay, so now let's look at one example. Impulse train. This is a periodic signal. Everybody agree? This is periodic. Anybody remembers the Fourier series for this one? Chapter 2. We had this impulse train, and the Fourier series was something very simple. straight line, no. It has to be discrete, D0, D1, D2. Look like that. Okay, if we go back to chapter 2, we had this, again, like fundamental frequencies, F0, 12, etc. And then we had 1 over T naught here, and then this was that. Now, based on what we have said right now, it says now if you take the Fourier transform, so this is Fourier series. So what do you think we have for Fourier transform? The same thing, instead of dots, you have deltas. Okay. So you have these impulses. And the height of them, all of them the same, meaning again the area, you know that the height of the impulse of that means the area or energy. And all of them have the same height or energy with 1 over T naught. Okay. So that's why we say if you have an impulse train in time, in the frequency also we have an impulse train. Okay. So next property of Fourier transform is when it applies to the convolution. And this is very, very interesting and property makes our life very easy. So what it says if you are convolving two signals in the time, okay, in the Fourier domain, the operation is corresponding to the multiplication in the Fourier domain. And this is really, really good because usually the convolution is hard, but multiplication is very simple. Okay, and now everybody might remember the definition of convolution. If you have GT convolved with WT integral of G of tau, WT minus tau d. This is the definition of convolution. And if you take the Fourier transform, interestingly, you just add it by multiply G of f, capital G of f by W. Okay. Now, from the duality, we have the second line that now if in a time domain instead of convolution I have multiplication, in the frequency domain I have convolution. See, therefore we conclude convolution in one domain is multiplication in another domain. So if you want to write it down, so convolution in one domain corresponds to multiplication in another. So convolution in the time means multiplication in the frequency. Convolution in the frequency, second line. Multiplication in the time. Okay, so again, this is very, very interesting. And just before I prove that, I give you one application. Can anybody think of an application that we have convolution? Or linear systems in general. Yes. So if you have, let's say, a signal G of t, you're gonna study this one. Alright. If it's applied to an LTI system H of t, and you get some output. So the output is equal to convolution, exactly. So the output of a linear system is convolution of G of t, and what do we call it? Or impulse response. So in the time domain it's a convolution. But if you look at, take a Fourier transform, in the Fourier domain, capital YF is equal to capital GF multiplied by capital H of F. Okay. And this is what we call transfer function. Probably you have seen before H of F. Therefore is Y of F divided by output divided by input. Maybe we have seen this before. But this is coming from this nice property of the Fourier transform. that converts this complex operation to simple multiplication. Now you appreciate Fourier transform, right? If you didn't have Fourier transform, we always have to do the convolution. Now we know Fourier transform, we convert the signal instead of considering the time. I take it to frequency and then do the simple multiplication instead of the convolution. But as far as the proof, I go details. Okay. So I'm going to prove the first line that if I convert two signals, and then if I take the Fourier transform of that, the Fourier transform is Fourier transform of this times Fourier transform of that. This is what I want to prove. Okay, so let's just follow step by step. So this is my signal. Let's say it is, I don't know, y. The Fourier transform of that is integral of y of t e to the power of minus j2 pi ft dt. Simple definition of the Fourier transform, right? Y of t times this exponential. Okay. Now let's extend the y of t, because y of t is convolution, right? Do the convolution. G of tau w t minus tau dt. Good. Now, this integral inside, what's the variable? Tau. Do you see any tau here? No. So basically, this is like a constant for this integral. And this is a very common trick. I mean, you will see it a lot of times. So try to remember this when you have this kind of integral and plot them together, etc. Usually, whatever is outside doesn't depend on that parameter, so I can take it easy. Okay. Good. See, now this is it. Okay. Now the second trick is that always in these cases we switch these two integrals, which corresponds to switching these two. Okay. We can do that because this integral is a linear operation. But okay, so this is the trick. So if you change these two, see, I change the order. Instead of d tau dt, I have t. Okay, now why we do that? Because if now I change these, a lot of things do not depend on t, and then I can take it out of the integral again. You know, so this is like a reverse. First we take this inside, and then we change the operation, and then we took the other ones out. Again, this is a very, very common trick. Okay, good. See, all this tau thing, g of tau, now can come out. And then, instead of these, I take amount of tau outside, and then this is remains. Okay, good. So, just looking at this, you see, okay, you have t minus tau, just a change of variable. And then, so I have the integral of w t prime e to the power of something. What is this? Anybody can tell me? Fourier transform. This is the Fourier transform of wt, which is capital Wx. Okay, good. Now, this is function of x. Now it can come outside, and then the rest. Now, what is this? The integral of g of tau e to the power minus j2 pi f tau. E tau.
Fourier transform
Another Fourier transform for now.
g tau.
G, very good. So that's why you get g of f times wf. Again, please go over this proof step by step, not to memorize it, but just to know the tricks, because you're gonna see these tricks everywhere. Very common tricks. You have two integrals, usually take one of them inside, change the order, then take the other one outside, and then usually now works out and becomes something very nice. Question? the takeaway is this second property, convolution and the multiplication. So now that we are considering convolution, let's see some of the properties of convolution. If I have two signals, let's say this signal and this signal. If I convolve it, anybody can tell me what happens to that? If I have two signals, start with the squares. If I have, let's say, from 0 to A, and then convolve this with something from 0 to B, what do you think the duration will be?
0 to B. Or 0 to A plus B.
Or in general, let's say if this is from A to B and then this is from C to D, what will be the duration? A plus, so the beginning, I add up together, A plus C, and then the end adds up together, B plus C. And to find out what's going on in between, I mean, it's a hard process. You have to, I mean, just overview. You have to reverse these and shift these and then overlap, do a lot of things. But the simplest thing that we can conclude is that always, when you do that, start from A plus C and end at B plus C. So somehow it stretches the signal. Okay. And so I guess if this is L1 and this is L2, this will end up to be L1 plus L2. So somehow add to the length of the signal. Okay. Please write this down. I mean, maybe you haven't noticed it from previous courses, but this is a very interesting property of convolution. Again, it doesn't matter what's going on between. It could be anything. So what happens, I can only say, okay, start from here and then end at this point. And then this is L1 plus L2, so that is the duration of this. So therefore, like in this case, if I start from 0 to A and the other one is 0 to B, when I convolve them, I'm gonna get 0 plus 0, so it starts at 0, then ends at A plus B. So now, why did we reminded that? Because let's say you have two signals, G1 and G2. G1 has bandwidth of B1 and G2 has bandwidth of B2. So you have G1 G that the band. When we talk about bandwidth, we are talking about the. So when I take the Fourier transform, the bandwidth, the maximum frequency is B1. Okay. And then the G2 has bandwidth of B. Take the Fourier transform, the bandwidth is B2. Because we have symmetry, so let's do 0 minus B1. So the bandwidth of this one is B1, the bandwidth of this one is B2. Now, if you have now multiplication of G1 times G2. Now the question is that what is the bandwidth of that? So if I take the Fourier transform, what happens to the Fourier transform here? Multiplication in the term is equivalent to
Convolution.
convolution. So basically I have G1F convolved with G2. With G1F with G2. So if I convolve these two, what I know is that these two are gonna be added together, so I'm gonna get B1 plus B2. Okay. So what happens to the bandwidth? The bandwidth is, so if the bandwidth was here B1 and here was B2, now my bandwidth is
Addition.
addition B1 plus B2. Okay, so this could be easily a question in the meter. I give you two signals. Let's say you find the Fourier transform of that from the table, and then I say what's the bandwidth of the G1 times G2. Okay, so it's just a simply addition of their bandwidth. So here, G1 times G2 has bandwidth of B1 plus B2, but this is the reason I didn't provide this, but please write it down. So this is the reason. For G1 you have the B1 and then B2, then you combine it with exponent. Okay, any questions? So what do you think will happen if if instead of multiplication the time, if I convolve them? If I have G1t convolved with G2t, which corresponds to multiplication with frequency. If I multiply these two, what will be the bandwidth? B1, the smallest. Yeah, if I multiply these two, the smallest will be the bandwidth. Again, this could be a question for the exam. And you don't have to memorize these things, you just have to look at, okay, I'm just convolving the time, check the multiplication, the frequency. So if one of them is B1, the other one is B2, and if B2 is greater, when I multiply these, basically it's going to be limited by just B1. Any question here? No? Okay. Next property, I guess, is the taking a derivative of the same. So see what happens to the Fourier transform. So if you have GT and Fourier transform is capital GF, then the Fourier transform of the derivative of that is just GF multiplied by J to 5. So do you remember a similar or something similar in the Laplace transform? If you take a derivative, what happens in the Laplace transform? This you should know because you had a circle, and in circle we use it a lot.
Multiply by S.
Yeah, that's it. And S. You remember I said what's S here? S is nothing just J omega or J 2 pi m. Okay. So yeah, so when in the second class when you had yeah, so dt, then it was S times G of S multiplied by S. Who remembers this? Yeah, I mean, even like when you're doing the circuit, you remember Ls for the inductor and then 1 over Cs for the capacitor. These are all because this is the derivative of the, I don't know, current or voltage, and this is the integral. So this multiplication coming from this property of the derivative, and then later on integral. The integral is 1 over S. Okay. Okay, so remember here, just S is always J2 pi f. If you make these connections, you're gonna remember both of them better. Okay, so again, it is like this. S times G of, there we have G of S, here we have G of S. And this is the integral. So 1 over S, so again, if this is like S, the integral is 1 over S plus something which is, anybody remembers the corresponding thing in the circuit? The initial value of the, I guess, the voltage of capacitor or something like that, right? V0, the voltage in the capacitor, we modeled this with 1 over Cs, and then I guess we had something like the V naught or something. The voltage, initial voltage in the capacitor, so that can be correspond. Okay, so I guess the proof is very, very easy. Just, if this is G of t, if you take the derivative of that, the derivative goes inside, and the derivative is with respect to t. It's power of j 2 pi f t. If you take the derivative of that, j 2 pi f times the rest, and this comes out of the integral, so that's it's very simple. And then we can extend this to multiple derivations, second order, third order, etc. So it's just s to the power of n, or j to the power f to the power n j. Any question here? So we are learning more and more of the properties of the Fourier transform, and then making connections with what we already know, and then what is in the practice, the mathematical formulation. Okay, so let's see one example. Let's say this is my geometry, triangular signal. Now take a derivative of that. What's the derivative of this one? Derivative of this is just the slope, which is 1 over, and when I do it, if I have a line, okay, the derivative is just the height divided by that, the slope. Okay, so in that case it's 1 over tau over 2. 1 divided by that is the slope of it. So that's why you get 2 over tau. So 1 over, no, this slope is positive. Yeah, so you only care about the length, but this is slope is positive. If we had the other way around, the slope was negative. For the other one. So a slope for this one, now again, this divided by that, but then because the slope is negative, so you get negative. Everybody follow me? I took a derivative of this. Derivative here is just the slope is constant, that's why you get a pulse here, and then negative of that. Now take another derivative. What's the derivative here? What's the slope here? 0. How about here? So basically everywhere is 0 except the jumps, the discontinuity. You see discontinuity here, you see discontinuity here, or a jump here, and a jump there. And I guess I talked about this in this class, that when you have a jump, and when you take the derivative, you're gonna end up with a delta. Okay, that's how you get 3 deltas. 1 delta for that, 1 delta for this, and 1 delta. Why this is downward, but this is negative. Or in other words, if I have something, let's say this is A, this is B, when I take the derivative, I say delta. What's the amount of the delta? Is E minus A times the delta. Okay, the amount of jump comes here as a scale. So now the jump here is from 2 over tau, and this is 0, right? That's how I get 2 over tau. Here the jump, here in the right side you have 0, here you have minus 2 over tau. So you get 0 minus this value, and then plus. Now look at here. These are basically the values. Here you have minus 2 over tau, and then minus, what's here? 2 over tau. So you get minus 4 over tau. That's how you get the negative going down one. Okay. So please write this down again, this might be helpful. So when you have discontinuity, when you take derivative, it's like the plus and minus, like the right and the left, B minus A. Find the corresponding delta. Okay, good. So therefore when I took twice the derivative of the B, this is why I ended up 2 over tau of this delta, and then minus 4 over tau delta t at 0, and then delta at t minus tau. So this is just 3 deltas together. Now from the properties of the Fourier transform, it says if you have twice the derivative, if you take the Fourier transform, you multiply it by s squared or j2 pi f squared times capital G. This is from the properties of the derivative. Everybody agrees? So this is one way to do that. Now, alternatively, I know that if I have this delta, what's the Fourier transform of that? What's the Fourier transform of delta t? Anybody remember? Very simple. 1. What's the Fourier transform of the shifted version? You know, always when you shift things, multiply by exponential. Okay. So that's how you get this minus 2 corresponds to the delta when you take the Fourier transform. This exponential corresponds to this, and then it corresponds to that. Everybody got this one? I had 3 deltas. I'm directly taking, see, this is the indirect way. Just make a note. Indirect. Meaning that I'm using property of derivative. This is indirect. Of finding the Fourier transform. Now, direct way, this is direct. Direct way. To look at each element and find its Fourier transform. This is 1, this is some exponential, then this is exponential. So, hopefully by now, when you see these 2 exponential together, it reminds you of a e to the power of j theta e minus j theta.
Cosine.
Cosine. So we get a cosine for that, and then just type this up at 2. So we get this. Okay. So now make these two equal because both of them are a full transform of same thing, just from two different methods. Okay. So again, I had this signal. I had two ways of Fourier transform: direct way and indirect way. Now they have to be equal, right? So make these two equal. Okay. So what do we get? J 2 pi f squared gf has to be equal to this. Tau cosine tau. So I guess the goal was to find g of f. So g of f is divided by that. Okay. So cosine of pi minus cos, and then tau pi squared f squared j squared. So make a note that you got these by this is A, this is B, equation or equation 1, equation 2, by the 1 equal this. Can anybody repeat me why 1 is equal to 2? Why these two equations I said they're equal? Because both of them are Fourier transform of the same signal. I just have different approaches, right? I use the property here, I use direct, so the same. So they have to be equal. I put them equal. This is what happens on GF. Okay, so do some math here. Instead of this, just mention sine squared. So this is the formula, and then this is the final thing that we want to say, that we got a sink squared. See, we have a sine squared divided by that, so I get a sink squared. So sink squared is a Fourier transform of a triangle. So this is what we want to find out. So let's not just basically practice of using this property. Okay, so therefore just write somewhere that, can I erase this part? Okay, no. Okay. By the way, I don't know if you know, but what's your name? Yes, he's recording the lectures, so it's available on YouTube. So in case you watch it later on, so.
There's also a Facebook group, like I think I post in discussion on web courses like in the beginning of the semester, and then I post links to it from there. So
Okay, that's good. Okay, so now the takeaway is that remember that we said if I have a pulse, the Fourier transform is the same. Now we add to that now if I have a triangle, the Fourier transform is sine squared. So when you square these, I mean, I will say similar, but now instead of negative, also you have positive, so it looks like that. See, this is the sine squared. Let me just prove it. Then with that triangle, we came up with the sine squared. Any question here? Can you think of another way of proving this? This was actually the hardest one. I don't know why they picked that. I guess probably just to practice this property. But to prove this thing squared is a very simpler approach. Triangle is two possible. What do you mean by that? Shift. What's the operation? What's the mathematical operation?
Convolution.
Convolution. Yeah, very good. So we know that if I convolve two pulses, so we know that if I convolve two pulses, I'm gonna get a triangle. Okay. Convolution of the equality. So now this is a convolution in the time. There are two pulses in the time, and this is also in the time. Now take a Fourier transform of this. Fourier transform of this is a C. Fourier transform of this also another C. Okay. You are convolving in the time. What do you do in the frequency? 1. So when you multiply these two, you get sec squared. And that is the corresponding to this triangle. Okay? Convolution in time, multiplication in the frequency. So in the time, convolve two pulses, you got a triangle. In the frequency, you multiply 2 sinks and you got sec squared. Everybody got it? Okay. Yeah, we have just few minutes left. Okay, just an overview of LTI system. I guess everybody knows that. So LTI system is a linear time invariant system, right? So linearity means that if you have some input, and then any, let's say, for example, if you have x1 and then x2, for x1 you get y1, and for x2 you get y2. Now if you apply, let's say, alpha x1 plus beta x2, if you apply superposition of the input, what do you get?
Alpha 1 plus alpha beta.
Very good. You get exactly the same superposition of the output. So alpha y1 plus beta y2. Right. Okay, for example, if you have twice x1, you're gonna get twice y1. If you have 3 times x2, you're gonna get 3 times x2, y2. And also addition of them, x1 plus x2, you get y1 plus y2. So this is in general. This is linearity. So the L comes from linearity. How about time invariance? Anybody can tell me what's the property of time invariance? In terms of English words.
Is it you're gonna get the same result with like t is t plus tau or whatever? Like if like any point in time, it's gonna be the same result.
Yeah, but
Yeah.
that's what, yeah.
It has to be one period shifted.
If you shift the signal, input signal, you're gonna get
Shifted
Shifted
output.
out.
Oh, okay, yeah.
So if I shift this, so if for example I have some timing bias. If I have xt, then I get y of t. Okay, so let's say whatever t is starting from 0, and then I get a sign from 0 t. And then if I shift the input, xt minus tau, let's say instead of starting at 0, I start at 5. The output is exactly shifted with the same amount, t minus tau. Okay, the same shift. The same shift in the input is the same shift in the output. So this is the timing variance comes. And put them together, you get LTI. Linear timing variance signal. And the interesting about the LTI systems is that this is actually really, really interesting. So what it says if you just apply impulse delta t to the system and look at the output, call it h of t, impulse response. Okay. If you have this information, h of t, now if you give me any input, I can give you the output by just convolving x of t by h of t. And this is a very, very interesting thing because if your system was not LTI, so I mean basically if you had to look at all the x's and look at basically you have to have a lookup table. If this is x1, this is y1, I change x, then you have to apply to the system and see what's going on. But for LTI, you only apply once delta t and you get h of t. After that, just any input, just is a convolution, as I said. That's very, very nice characteristic. So therefore, when we talk about an LTI system, we only represent it with the impulse response because that's the only information I need to know about the system. Then what happens to the system if I apply an impulse? And then any other input is just gonna be the convolution. Okay, and based on the Fourier transform property, we just learned that convolution the time is multiplication the frequency. So basically y of f is nothing but just h of f, which is Fourier transform of the h of t plus x of t. So I guess I stop here. Then continue next. Again, you have the homework. Go to web courses and
You said the quiz will be Monday?
Yeah.
Okay.